In this practice, a 200 kg merry-go-round in the shape of uniform solid horizontal disc of radius 2 meters is set in motion by wrapping a rope about the rim of the disc and pulling on the rope. The merry-go-round rotates from rest to an angular speed of 1 revolution per second in 5 seconds. Calculate the force exerted on the rope. So maybe I'd like to draw the figures at first. The merry-go-round, a disc with a radius of the R, and the rope is pulling with the force of the F. Then at first I'd like to find out the moment of inertia of the disc. Moment of inertia of a disc is a constant density. We can consider the contribution from the ring. Ring width is R, and the distance from the center of the disc is R. This is dr. The mass inside of these rings can be expressed dm. 2 pi r is a circumference of the ring times dr. This is area of the ring times surface density. This is surface density. If you multiply surface density and areas, you will get the mass inside of the ring. Then we'd like to find out the moment of inertia. Is r square dm. This is the definitions of the moment of inertia. Then you can substitute this dm here. Then it becomes r squared times 2 pi r sigma dr. And r is changing from the 0 to the capital radius of a disk. Then you could perform the integrals. 2 pi sigma is a constant value times r cubed, so it becomes 1 over 4 r to the fourth, 0 to the r. So it becomes 1 over 2 pi sigma r to the fourth. The total mass of the disk is given by sigma r squared. So if you use these expressions here, then it becomes 1 over 2. No, you have to multiply the pi m r squared. This is the moment of inertia of the disk. Then in these questions, the merry-go-round has a mass of the 200 kilograms. And the radius is 2 meters. Then you can find out the moment of inertia of the disk. 1 over 2 m r squared. You can substitute here and here. Then it becomes 400 kilogram square meters. This is the moment of inertia of a disk, merry-go-round. Then from the questions, actually the merry-go-round rotates from rest to the angular speed of the 1 revolution per second in 5 seconds. So omega is actually the t equals 0. Omega is 0. In the 5 seconds, it becomes 1 revolution per second. So omega is increasing with times. So we'd like to find the angular acceleration from these data. Alpha is a delta omega over delta t. This is the angular accelerations. So delta omega is 1 revolution per second over 5 seconds. And the 1 revolution is a 2 pi radians. Then you can write down that this is 2 pi over 5 radian per square second. This is alpha. In the equation of motion for rigid body rotations, rigid body rotation. You can remember this is I is a moment of inertia times angular acceleration equal torque. This is the equation of motion for rigid body rotations. And then we discovered I is a 400 kilogram square meters. Alpha is a 2 pi over 5 radian per square second. Then torque. This torque, if you look at these figures, from this torque R times F, and in this case it's angles between the two vectors is right angles. So torque is expressed R times F because of sine 90 degrees. Is sine 90 degrees 1. Okay, then question is we'd like to find out force. This force exerted on the rope. So from this equation you can find that F is expressed I alpha over R. And if you substitute numbers, I is 400 square meters, alpha is this numbers, R is 2 meters. Then you will get 251 newtons. This is the answer to this practice.